In this video, I want to think carefully about one idea, vector-valued functions, or VVFs. By the end, I hope this idea feels more simpler and more connected. So, what is a vector-valued function? Before talking about it, I want to review just briefly about what a function is. As many of you already know what function is, it's just a switch, you know. There's an input, and if you press the switch, it does something. So there's an output. So in single variable calculus, a function, we usually write it as f of, let's say, x, and this gives an output, right? And this function is usually, this output is usually just a number. A number in single variable calculus. So in other words, it's just a scalar function. However, in multivariable calculus, when it comes to vector-valued functions, it gives an output. So we usually write it as r of t, and this is a vector, and this gives a vector. So instead of assigning a number to each output, we assign a vector. And vector-valued functions, or VVF, it describes motion in space. Alright, now let's talk about definition of vector-valued functions. By the definition, we can say a vector-valued function is a function whose output is a vector. In 2 dimensions, vector-valued function r of t is x of t and y of t. In 3D, r of t is x of t, y of t, and z of t. We just needed to add one more component, which is z component. So these are the vector-valued functions in 2 dimensions or 3 dimensions. And as you can see, each component are just ordinary functions of t. Alright, let me give you an example. We are given a vector-valued function, r of t, which is equal to cosine of t, sine of t, and t. As you may wonder, I have drawn sine functions and cosine function here. So these look like this. And let's figure out what does this vector-valued function look like in xyz space. So first, let's see what happens at t equals 0. Then r of 0 is equal to cosine of 0 is 1, sine of 0 is 0, 0, right? And let's see one more. At t equals pi over 2, or 90 degrees, r of pi over 2 is equal to 0, 1, 1, right? So as x and y moves in circle, the z component increases steadily. In other words, it traces a helix. Now let's see what it looks like in xyz plane. Let's see how it looks like geometrically. Let me draw xyz space. Alright, there's x and z and y. Let's say this is a 1. So x and y components draws a circle, right? It's like a unicircle. And the z component, it goes up steadily. So it should look like a helix. So it should look like this. Interesting, right? We just talked about vector-valued functions and how they work, right? So why they are important, why they are useful. They are useful because they package, a VVF package multiple coordinates into one object, which is good. And they make geometry easier to see, as you have observed in the earlier helix example, right? And lastly, they work so naturally with derivatives and integrals. So this is why VVFs are useful, and also I'm sure it will help you to understand next chapters that we're going to cover soon. Speaking of it, in the next video, I'm going to talk about arc lengths in multivariable calculus, not in single variable calculus, which will be more interesting. So until then, let's keep things simply connected. Thank you.